Is that what you're talking about? Or something more general?
Single field, and all the interactions are phi dot to some power.
Okay.
So they break.
But you want to have exchanges involving phi as well.
Only involving phi.
Yeah. Okay.
I mean, in some sense, it's not this like the super interesting theories, but it is not Lorentz invariant. Right. It's not invariant. However, it is related to the conformally coupled. So it's a way to get something non-boost invariant out of something boost invariant.
Right.
But sorry, Enrico, will there be some accidental symmetry then if it's related to conformally coupled? Because we know that they have full de Sitter symmetries, right? I'm confused because you are writing something that is manifestly Lorentz violating, but you're claiming that it's related to something that is fully de Sitter invariance.
I mean, the answer is much simpler than all the other answers. Every time you put special derivatives, you get a million terms. Question.
I think probably the point is that whatever differential operator generates this thing won't commute with the de Sitter isometries. So by acting with it, you could generate something not de Sitter invariant.
But do you think this will appear once you consider exchanges? Because if it's at the contact level, if all you're feeding in are conformally coupled mode functions, then I'm just confused.
Yeah, I think probably the subtlety is with the exchange.
Mm-hmm. I see.
It just seems to be kind of the next interesting class of toy models that goes beyond the conformally coupled, but not very much, and is relevant because that's like the #1 target on non-Gaussianity.
But actually, can I ask for some clarification? You guys were saying that you think that 4-point exchanges should be totally fixed by the optical theorem. I guess you must mean that plus information about like total energy and partial energy singularities, right?
We meant up to contact terms. The statement for up to contact terms.
Yes, but also inputting information about, say, partial energy singularities.
No, so I think that the only thing that you should know is that what do you mean by contact term? So if you know what you mean by contact term, meaning that it shouldn't have any singularity like E left, E right.
Yeah, I think that can't be right then, because there are solutions to your optical theorem 4-point relation that aren't the right answer because they don't have the right partial energy singularities.
Even the cubic.
The factorization that you just derived in your paper, it's a consequence of this optical theorem.
I don't think so. Yeah, I can show you some simple examples that solve your relation, but don't have the right E left, E right singularities. They're in fact these like two-side graph kind of examples.
Yeah, I'll be very surprised because I mean, what example exactly?
Yeah, so a very simple example is like one over K1 plus K2 plus S times 1 over K1 plus K2 minus S times 1 over K3 plus K4 plus S. That will satisfy your relation, but it has the wrong, in particular, it doesn't have a total energy singularity, and it doesn't have the right factorization singularities.
Yeah, I think that what you're saying has the bad singularities, right? So you should.
Yeah, but good. So that's exactly what I'm asking. So you must be putting other information.
Yeah, you need some input from like what sort of singularity is allowed, which.
Good.
Which a priori doesn't have anything to do with unitarity. So I would say that it is fair to say that. I mean, you don't have like collinear.
I'm just trying to understand what the rules are.
Exactly. This thing that you just suggest, when you put it on the left, this is what you should put on the left-hand side, your example, right?
Yeah. It'll reproduce the correct right-hand side.
And the right-hand side, it gives you 0, or what does it give you?
Oh, no, it gives you this double shifted wave function thing on the right-hand side.
I mean, what you can easily prove is that if you take two solutions of that equation and you subtract them, the difference obeys left-hand side equals 0. So
yeah, I can check that, but it differs from the true solution by something which both has a total energy singularity and I think some folded singularity. So if you're forbidding folded singularities from the jump, then of course I agree.
I think when we say up to contact, by contact we mean something that obeys psi4 plus psi4 star equals 0. And then it must be true.
But is what
Okay,
you
I
guys
mean,
are
yeah, we can look more at the details. It's kind of some technical thing. But
In recovering the poles in the subdiagram poles, we did have to assume that we didn't have any of the collinear singularities, because otherwise the second term can be what gives you the pole on the right hand side, and so that's an extra thing that you needed to get the
yeah.
So,
That's also what I
Yeah,
agree with that.
yeah, I think I agree with you. So actually, so I don't know, is it now the time for discussions, or we are smoothly connecting to the discussions, or not yet?
Discontinuing.
Go ahead, Liz. Good idea, basically.
but are you saying that you know where this, if you, is the point that you input knowledge of where the singularities are, and then you have a bunch of undetermined constants that are fixed completely by your relation? Would that be correct, or is it?
Yes.
Okay.
Yeah.
Okay.
Yeah, up to contact terms, as I said. So
Yeah. Okay.
stuff that have KT singularity.
Okay.
Yeah, and actually I checked, there were some cases when we were doing this factorization business that there were some, much like Enrico was saying, there are sort of some subleading poles that go along with the leading total energy singularity. And in some cases, you can appeal to conformal invariance to fix them, but also if you require this optical theorem relation, you do find that those singularities get fixed by, or sorry, those coefficients get fixed by this relation. And it's not totally crazy, because it's basically the reason that those poles are there is something about the structure of the bulk-to-bulk propagator. And also the optical theorem is telling you something about how the bulk-to-bulk propagator gets cut. So it's like putting in some additional piece of information that fixes these subleading poles.
But if what you guys are saying, if it works the way you guys are saying, I'd like to understand what occurs, say, just for conformally coupled scalars exchanging a conformally coupled scalar, because this couldn't fix it, I'm pretty sure, because you just lose this information, because you have a completely factorized thing on the right-hand side, whereas the full answer is this tangled dialogue.
Yeah. So I think everything I'm saying is for where everything is rational. When you have logs and dialogues, then I think it's much more complicated.
Right.
I'm not sure.
I don't see conceptually the discontinuity there.
I see. But actually, maybe I can ask you a question sort of related to what Nima was asking. So the way that you sort of integrate the symbol to lift it to a de Sitter 4-point function is in some sense channel by channel, whereas the dream would be, so like Hayden was saying, we have sort of cases where you are required to introduce multiple channels in order to have a totally consistent object.
Right.
And in principle, you can kind of break that object apart and integrate it sort of channel by channel to get the Sitter answer. But the dream would be to have some operation that you do to the total object in order to build the de Sitter answer. Do you have some ideas of what this type of operation could be like? Or have you thought about it?
I've played with it. One thing I played with was trying to do the multiple channels cosmological polytope, which I found a canonical form with a pullback that seemed like it would work, but the geometry was nonsense. It was like it would be start with a bounded square, but then took away two opposite corners, and it was just a terrible geometry. So I think I just hacked together a form, but didn't. But I don't know if that was on the right track. But other than that, no, I haven't found anything useful to say. I've started to play also with the like 4-gluon correlator to see that it's just go through like the 4-particle test. And in flat space, the kinematics are so nice, it just falls on your lap. But I'm sure you guys have played with it a lot. The singularities there's no obvious simplifications largely due to just the details of the spinor helicity variables, and just
Yeah,
don't
we
have
should
the
talk about
same-
it because I've also played with this this example.
Yeah,
It's a kind of a nightmare, but we should talk about it.
It seems to me
Sure,
that this
great.
Actually, Aaron, can I ask something related? I think it's closely related to Austin's question. So this,
Yeah.
because I was very intrigued by your final recursion relation, but that one still also works channel by channel. Is that right? Or am I missing?
Yeah, it's just a graph by graph statement.
Yeah, because actually the dream is actually, I just learned from actually Wei Ming Cheng explained to me how BCFW works for Compton scattering. And there's the case that you just have to form the form S and T channel, and you get the U channel and the contact for free. So it's kind of like it's really a mixing. BCFW recursion really mixes the channels, and the hardest part of the amplitudes you're actually getting for free. And so that's really what would be nice to do for a cosmological correlator, where you're kind of deforming simple channels that then give you contact, which are often very hard for gravitational or spinning fields.
Right.
Somehow for free. But so if anybody has a recursion relation that has that feature, I'd like to see it. But,
yeah.
I guess
this is a graph by graph statement.
I see. But then also, another question
what
I
you
have
said, Daniel, is even true. I mean, it's true for every case where BCFW is interesting. I mean, it's even for gluons, for everything.
Yes. I just learned. Yeah, just learned it for Compton scattering, which was amazing enough for me.
Right.
Yes.
I mean, that I think it is related, but presumably you can see it. I mean, it's just the fact that you see in the amplitude, however you get it, that there's no that when you get the final amplitude, it does not look like a sum over channels when you have gluons and gravitons. It looks like 1 over STU or 1 over ST. That's the defect. That's the kind of a representation invariant fact that the amplitude does not split into a sum over channels unless you break Lorentz invariance. So and presumably you see that even in the examples that you guys have worked out. You must see that the actual correlator does not split into a sum of channels. Yeah. So once
that's kind of the annoying thing.
Huh?
Is so it's kind of annoying actually in correlators that there's always like a total energy singularity, which is the amplitude, which is of course some irreducible thing. But then there are always other pieces that you need to get the partial energy singularities right that you can't like group into one irreducible object.
I see.
Or at least we haven't found a way to do it.
Are they invariantly given, or are they representation dependent somehow? Or are they completely invariant?
Sorry, invariant under what?
Well, I mean, do they involve any choices how you write it?
Not really. I mean, there are always some ambiguities about spinor algebra and Schouten identities and stuff like that, but they're totally fixed by the singularity structure.
Right. I guess just at the logistical level, I guess we are already into the discussion.
Yeah, that's what I was going to ask to Paul, who is the chair. Like we are already deep. We're probably over time with the discussion session.
Feel free to lead the discussion whichever way. Just want to be sure. I mean, the talks for this session were also collaborators of Hayden, so I think that they have been more or less involved in the discussion so far, Austin and Carlos, but if there are people that have specific discussions about their talks, and we also had some question for Aaron, but I think those were the talks that we were supposed to.
Right. Well, and Paul's talk also, but maybe if Costas is leading the discussion at the end of the day, so maybe you can talk about Paul's talk more in detail later. If you, I don't know, however you prefer.
Yeah, sounds good.
I mean, this makes some sense. Yes, I think we can start with that in the discussion at the end of the day.
Sounds good. Yeah, regarding your question about counting costs, I think it's interesting. As far as I know, I think Carlos looked into this. I don't think even the flat space S matrices have been fully understood for contact interactions. So.
No, I mean, I agree. And also I've seen Minuala's talk at strengths that looks like, in a sense, he's getting at least the flat space 4-point scattering amplitudes for gravitons.
Yeah.
So it should be something analogous for the 4-point functions.
Right.
But it is important to understand, what is the vector space where we actually solve for the correlator.
Yeah, it could be that this counting by Tolya-Dzimarsky, for example, it could be that there are structures that never correspond to a 3-level contact interaction, and that would be a possibility also, that even if you did the counting, you would still be missing some stuff. Right?
Sorry, what is the question? Is the question what all the independent
structures for J or for T correlator?
Yep. I mean, it's not an easy problem. Even the counting, even Damascus counting is not a walk in the park.
Well, it's a trivial problem for amplitudes. So I'm not sure what the Sorry, maybe I misunderstood the discussion a second ago. It's a completely trivial problem for amplitudes.
For graviton, so look for graviton.
Trivial. Write down any expression
level.
in terms of lambdas and lambda tildes. You're done. If you want to do it in higher dimensions, use helicity variables in higher dimensions. I mean,
no. In any way, sorry. Why is it a trivial problem? It's by just counting.
Write down any expression in terms of lambdas and lambda tildes. You're done. They're all independent. You're done.
You need to impose conservation or gauge invariance.
No, there's no gauge invariance. That's the point. When you spin helicity variables, you don't have gauge invariance. That's the entire point. So that's the whole point of using these variables. The problem is utterly trivial. It certainly in dimensions it's utterly trivial. I'm not sure. In 6 dimensions and 10 dimensions, it's also quite straightforward.
So what is the expression given in 4 dimensions?
Expression in terms of lambdas and lambda tildes that has the correct helicity weights is
not just 3-level, right? The general, not just.
No, it doesn't matter. I mean, yeah. So that in fact, a completely you want 4-point functions. Let's say plus plus minus minus for gravitons. You'd write down 1 2 to the 4th, angle bracket 1 2 to the 4th, square bracket 3 4 to the 4th times any function of st and u. That's the most general expression you could have. And there's no thought. Then there's no gauge invariance, nothing. It's a complete triviality. I mean, I'm calling it a triviality just to emphasize this is the conceptual point of the spinor helicity variable. So, but I guess the analog for correlators is more complicated because it's more complicated to impose.
I mean, also why you cannot use metrics when you construct the tensor structure.
Sorry?
Why you cannot use metrics? I mean, you use, in a sense, momenta in terms of helicity spinors, but the right-hand side could also contain the most general structure. Okay, you can do it in the helicity basis, whatever you want. If you do it, let's say, in momentum space, you need the most general expression that you can construct containing metric and momenta. And then you can just do a counting of how many possible terms you can have. And I think for 4-point functions, it's something like 600 terms you can write down. Now, of course, if you use
statement, right? This is a dimension-dependent statement. I mean,
I think you're already in 4 dimensions. Yeah, of course, it is dimension-dependent. Yes, absolutely. Yeah. And there are also the generalists in different dimensions.
Right, right.
And there are also the generalists in different dimensions. But I think you're already in 4 dimensions. Yeah, of course, it is dimension dependent. Yes, absolutely. And there are also the generalists in different dimensions. But then
that's why I make this point. I think that I think this. Is it possible to write here, guys?
Yeah, just a second. I need to make you host.
Oh yes, if you're a host, you can share your screen or tablet or what it is.
I think doing it in general dimensions is more interesting, and I don't know. But I just let me just say quickly. This I just want to make because it's not. I just so 100% backward that you can go back and forth between the amplitude and the operators trivially. So that. Yeah. So just the point is the following. Just quickly. So so let's say you want to do gravitons. I want to let's say classify possible contact terms involving gravitons. Fine. Now the point is that the amplitudes.
I was not just discussing contact terms, but of course you can start with contact terms. So
you can do anything. You can do anything you want. I can multiply it by any function of ST and U I like. But what I want to do is, but the point is that the amplitudes of the things that are invariant, field your definition invariant, you have to worry about equations of motion, blah blah blah, right? So we can just write down the amplitudes, and for any set of helicities on the outside. Let's say I'm doing this one, but we can do it for any set of helicities on the outside. The most general thing you can have for this is 1, 2 to the 4th, 3, 4 to the 4th, just something that has the correct helicity weights times some function of ST and U. That's it. That's the most general thing you can have. And we can actually, if you want to translate this into some, so that's the most general structure you can have. If this function is a polynomial, if it's contact terms, then we can also sort of uniquely associate them, canonically associate them to operators in the effective action. So that's the only other tiny point I wanted to make. So let's say I'll just do an example with fewer indices. That the point is that we can write f mu nu. We're in 4 dimensions, so we can write f mu nu first as f plus mu nu plus f minus mu nu. So where f plus or minus is f mu nu plus or minus f dual mu nu, right? Maybe with an I. But the nice thing is that f plus and f minus are directly expressible in terms of the spinor helicity variables. So so just if you have f alpha beta alpha dot beta dot, which is my f mu nu, then for plus helicity, this would be epsilon alpha beta lambda tilde alpha dot lambda tilde beta dot. So for instance, if I have an expression that looks like 1, 3 to the 4th, I immediately know that this expression is actually f plus mu nu f plus mu nu squared. I instantly know that. And so in this way, you can take any expression in terms of spinor helicity variables and actually just convert it to some operators instantly. So this sort of going back and forth between contact operators and the corresponding spinor helicity variables is trivial. But that's, if you don't have contact operators, that's fine. You just write down any function of S, T, and U. And so that counting is, so that's it. For amplitude, it's trivial. I think for correlators, it's not trivial for the usual reason that we don't know, other than imposing these differential operators, we don't know how to check for conformal invariance. So we have to write these.
Nima, yeah. Massimo Tarona is mentioning that people working in higher spin gravity in ADS, yeah, they have built some bases. So it would be interesting to.
Basically, there is you can everything that you can do in flat space. It is any amplitude, any contact term in flat space. You can find an associated anti-de Sitter vertex or contact term in anti-de Sitter, and therefore in the circuit. It's really easy to see how to go from one to the other.
Does it agree with the counting of the masking?
Yeah. The basis
There is an
is
explicit basis. There is an explicit basis, not just counting.
So the point is that since the analysis that has been done by the airspeed community starts from a dimensional, arbitrary dimensional analysis, and then in each dimension, then you can also look for dimensional dependent identities and so on. So because of that, I don't remember if Timarsky he also classifies parity violating structures, but there are various subsets of this type.
Let's put aside the parity violating ones, which are more.
All of these. So for the going from flat space to anti-de Sitter, maybe for the parity violating ones, there is still some subtlety to clean up. But for at least for all the parity preserving ones, there is a clear mapping how to go from one to the other, and also an understanding of dimensional dependent identities in each dimension from